Welcome to the first class in this number theory course that actually does some content. This is the first class where we get our hands dirty. We'll be talking about a few proofs also, because certainly in an advanced class such as this one, anything that we claim has to be proved or at least justified in a certain way. And we'll be talking about numbers and sequences here. Well, so first of all, you could say, well, it's no surprise that we talk about numbers, because what other than numbers would number theory be about? But we're already lumping in sequences here because we need sequences of numbers anytime we talk about more than just one number. Number systems are needed as the surrounding universe for our arguments, but we'll be informal here in introducing the number systems. And if you really are interested in the formal constructions, I've got another course for you. It's called Fundamentals of Mathematics. The slides are and the videos are on my website, and I've even written a book that you can buy. Okay, so number systems. Basically, the integers are just the whole numbers. They are the numbers in a set that counts 0, 1, 2, 3, and so on, but which also includes the negatives of these numbers. And that definition is certainly very, very informal, but we do need a starting point. And our starting point will be that we assume that we know what integers are and how they work. So I'm not going to define what addition and subtraction is. I'm not going to define what multiplication is, and so on. And you may think, wait a minute, we have to define that. And yes, technically we would have to define that, and that's one of the things that the Fundamentals of Mathematics course is about. So we assume that we know addition, multiplication, and ordering, and all those other things. And well, then we can also state the following. It's called the well-ordering theorem, and that well-ordering theorem says every non-empty set of positive integers, so if we start at 1, 2, and so on, every non-empty set of these things has a smallest element. That also feels very reasonable, because if you give me a set of positive numbers, I pick one number, and if that number is not the smallest number, well, I've got only finitely many possibilities underneath that number. I check them all, one of them will be the smallest element. So it is a bit surprising that in a more formal introduction, when you actually construct the integers in set theory, that this can actually be proved and actually has to be proved. But in this course, we will use this as an axiom, and the quick justification I gave is probably as good as it gets here, and it's fairly convincing. I mean, you've got finitely many possibilities, and one of them will be it. And using the well-ordering theorem as an axiom is also often done, so we are not losing anything here on the formal side. Okay, so the number system that we are most familiar with certainly are the real numbers. And we're just going to assume that we have some idea what the real numbers are, because we're really not going to work much with the real numbers. And we're going to call a real number rational if and only if it's a fraction, which is if and only if there are integers numerator and denominator, so that the denominator is not 0 and x is the quotient of numerator and denominator. The set of rational numbers will be denoted Q for quotient. The set of real numbers will be denoted R for real numbers. The set of positive integers will be called Z+. And if you're wondering about the Z, well, that Z actually is, well, the word integers doesn't start with Z. We know that. Z stands for the German word Zahlen, because apparently the notation was invented in Germany, I would think, and then taken over by other mathematicians here. Otherwise, we would probably call these things I, but once something has become fairly customary in mathematics, we stay with it. Okay, so positive integers are Z+, and or we could call them in for natural numbers. I typically prefer in for natural numbers there, but we'll see, and we'll use it anyway. It counts. All right, so let's prove something, or let's at least state something. Yeah, we're going to prove something, and that is there is no rational number such as r squared equals 2. So this is a typical thing that you often see in a first proof class. It's one of the first proofs that people can do, and it's a surprising thing, because basically it says that square root of 2 is not a fraction. Well, how do you prove that? Okay, we take n element n. Okay, so we're going to feel free to use what is called set notation, and so n element n just means that n is a positive integer. And so first we're going to talk about a natural number whose square is twice another natural number. So we're not going to talk about this stuff at all. Basically, we could have said split this off as a lemma. But we're first going to talk about numbers whose square is even. Well, that means that 2 is a factor in the prime factorization of n squared, right? And we haven't really proved anything about the prime factorization yet, but we will eventually, and for right now we just assume that there is a prime factorization and we know a few things about it. But every factor in the prime factorization of a square occurs with an even exponent, right? Because we know that when you square something, you multiply all the exponent by 2. Okay, so that means that n squared is actually 2 squared times k squared for some k. That k may have more factors 2 hidden in them, but what we're really interested in is just the 2 squared. Because basically that means that n is equal to 2k. And that means that if n squared is divisible by 2, then so is n. Okay, haven't talked about rational numbers at all, but sometimes, and you will also see that when you read proofs, proofs start out with something else. And when proofs can start out with something else. They don't always do. But when that happens, you just work your way through that part, because the clouds should ultimately part, and the clouds ought to part in the second half on this slide. Because now we suppose for a contradiction that there is an integer n and a natural number d, a denominator, so that n over d quantity squared is 2. So we suppose for a contradiction that this statement is wrong. That's a standard proof method. And basically what you do in a proof by contradiction is you assume the contrary of what you want to prove, and you derive something from it that can't be true. And because we know that something that is true cannot imply that something that is false, this assumption that we made for a contradiction must have been false, and that means that there cannot be n and z such that n and d so that n over d squared is equal to 2. Okay, we'll see that as it flows along. So let's just assume right now that n over d squared is equal to 2. Well, without lots of generality, we can assume that n and d have no common factors and that n is a natural number, because after all, the square erases negative signs, so it doesn't matter if we have negative signs inside the square. And we also know from the way rational numbers work that we can't take a fraction in what is called lowest terms, and that means that numerator and denominator have no common factors. But that would then mean that n squared is equal to 2d squared, right? Just multiply the d squared over. And that implies that n is equal to 2 times another number, because if the square of n is 2 times a number, then n is even. So n is 2 times n2. But that means now that 2d squared, which is n squared, is equal to n2 times 2 squared, which means that, well, 2d squared is 4 times n2 squared, which means that d squared is 2 times n2 squared. And that means the square of d is even, and that means that d must be even. But that means that 2 divides, this thing is called divides, that 2 divides n and 2 divides d, and that's a contradiction. Okay. So that's a first proof in this class. If this is your first proof class, don't get scared quite yet. I mean, you do get used to proofs as we are going along with the structures, but at the same time also be warned, you really have to argue your way through quite a few things in this class, and well, you will come out of it actually a good bit stronger than you went in. But the transition, and I've worked on the transition to proofs, on teaching people how to do proofs for quite a while now, and no matter what we do, it is always a jump from calculus and other things, so just bear with me, trust me. Okay, so this proof here, basically what happened in the structure was we assumed for a contradiction that what we wanted to prove was wrong. And we came up with something that can't be true, because on one hand, n and d have no common factors, and on the other hand, so on one hand, n and d have no common factors, and on the other hand, 2 divides both of them. That can't be. Okay, the only way that can happen is that what we started out with is wrong. And what we started out with was that there are these 2 numbers, so that n over d quantity squared is 2, and that means there can't be any 2 such numbers, and that means there can't be a rational number whose square is 2. All right, now let's see what we can do with real numbers. Basically, for every real number, the symbol bracket x or floor x denotes the largest integer that is less than or equal to x. So basically, if you think of a real number as a decimal, then floor x just cuts off the decimal part. And as a function, this thing is then called the greatest integer function. It's a very common function to work with. And well, what that means is that for every real number x, we have that the greatest integer below x is less than or equal than x, and that's strictly smaller than the greatest integer below x plus 1. On the other hand, we can then also define the fractional part, and so for every real number x, we will say that the fractional part of x is x minus the greatest integer below x, and that's called the fractional part of x. As an example, the greatest integer below 3.4, the floor of 3.4 is 3, and the fractional part of 3.4 is of course 0.4. We have to be a bit careful because the greatest integer below negative 4.8 is negative 5, right? Because on the negative axis, we still have to go to the left and the absolute values get larger. And that also means then that the fractional part of negative 4.8 actually is 4.2. Not 4.2, 0.2 for goodness sakes. Okay, well, what we can do then is we can talk about a real number and an integer, and we can talk about a few properties of the greatest integer function. And so, for example, the greatest integer below x plus n is the greatest integer below x plus n, and that's fairly simple to prove because when x, we know that x is the greatest integer below x plus the fractional part of x, and that means that the greatest integer below x plus n is the greatest integer below the greatest integer below x plus the fractional part of x plus n. And these two things are integers, right? And so they go away in the fractional part. And so these two are integers, and this is the only fractional part. So if I rewrite that as greatest integer below x plus n plus the fractional part of x, then we realize this is an integer, and this is a fraction between 0 and 1, 1 excluded. And that means that the greatest integer function that is on the outside, this floor function that is on the outside, cuts off this fractional part, and we end up with the greatest integer below x plus n. And that is what we claimed. All right. Well, that proof was a whole lot simpler, I hope, but it shows something else that we have to do when we write up proofs, and that is called meaningful symbol manipulations. You see, what we have done here, as we worked our way through this computation, through this thing step by step, we had to know what the symbols meant in order to understand why this is an equation, why this is an equation, and why that is an equation. And so that is something else that is underlying to proofs. And we move on. Well, now we're talking about Diophantine approximation, which is, if you want to have a really lax definition of it, is anything that uses integers to approximate stuff that doesn't work with integers. And well, the pigeonhole principle is not among it. The pigeonhole principle will be a lemma for what we're going to prove, which is called one of Dirichlet's theorems. So what is the pigeonhole principle? If you've got k plus 1 or more objects and they are placed into k boxes, then at least one box contains at least two objects. Well, that makes sense, right? I've got too much stuff and not enough boxes, so some box has to be double booked at least. And to turn that into a proof, you suppose for a contradiction that each of the k boxes contains at most one object. Well, then there would be at most k object, right? K boxes times at most one object, but k is strictly smaller than k plus 1, and here's our contradiction. And that's it. Okay, so proofs can be fairly simple. This proof, however, was a down payment to the following, to what is called Dirichlet's approximation theorem. And well, we want to talk about a real number alpha, and we let n be a positive integer. And we are saying that then there are integers a and b, so that a is between 1 and n, and a alpha minus b is smaller than 1 over n. The reason why that is then an approximation theorem basically is because if you divide by a, you end up with the fact that alpha minus b over a, and b over a is a rational number, that distance is also smaller than 1 over n, and that basically means that for every real number you can find rational numbers that are arbitrarily close. And that is rather important because rational numbers are something we can represent with integers, whereas real numbers, when you really think about it, are actually quite complicated because they are infinite non-repeating decimals, right? Okay, so what's the proof for this? We'll prove the result only for alpha greater than 0. That's another common strategy because, well, basically for alpha smaller than 0, we could technically just add another integer and turn it into a positive number, then do the approximation, and then shift things back to the negative axis. So we're only going to prove it for alpha greater than 0. And we're going to consider the numbers a alpha, and here we have to be careful because a alpha is the fractional part of a alpha here, where a is in the set of numbers from 1 through n. Well, if none of these numbers is smaller than 1 over n, well, then we've got n numbers in boxes, right? The box from 0 to 1 over n, from 1 over n to 2 over n, from 2 over n to 3 over n, and so on, all the way to n minus 1 over n to n over n, which is 1. So when that happens, then there must be distinct numbers a1 and a2 between 1 and n, and a j between 2 and n minus 1, so that a1 alpha and a2 alpha are in j over n, j plus 1 over n, and those should be the fractional parts. So hang on just a second here. And we're back. Okay, so these fractional parts must be in the same little interval here. Okay, we ought to be able to get something out of that, because now if the fractional part of a2 alpha is greater than the fractional part of a1 alpha, and if also a2 is greater than a1, well, then we have that the fractional part of a2 minus a1 times alpha, well, that's just the fractional part of a2 alpha minus the fractional part of a1 alpha, and that's smaller than 1 over n because those two are both in the same interval here. And that's a contradiction because a2 minus a1 is in the set 1 through n, because those two numbers are different from each other, but neither one of them is bigger than n. Similarly, it's also not possible that a1 alpha is greater than a2 alpha and a1 is greater than a2. And so that means that we must have an a between 1 and n so that a alpha is smaller than 1 over n. Okay, you've noticed that I've paused here for a second, and that is because there are a couple more cases here, and that is that it could also be that a2 alpha fractional part is greater than a1 alpha fractional part, and this inequality is flipped, and similarly it could be that this inequality is true and this inequality is flipped, but in any of these cases we can do a similar computation and get a contradiction. So that means there is an a between 1 and n so that the fractional part of a alpha is smaller than 1 over n. And once we've got that, we just set b equal to the greatest integer below a alpha, and we obtain that a alpha minus b, absolute value, well, that's a alpha fractional part plus greatest integer below a alpha minus b, which is the greatest integer below a alpha, and you realize these two cancel. That's the absolute value of the fractional part of a alpha, and that was smaller than n, and that means we have Dirichlet's approximation theorem. Sorry about the hiccup here. This is another thing that you will see in proofs. Okay, certainly not hiccups on purpose, but sometimes that does happen. But what you will also see in proofs, written as well as in presentation, is that certain parts are being left out for the reader to fill in, and certainly this is something, even though I was stuttering my way through this a little bit, this is something where I certainly want you to take a look at these cases and convince yourself that you can fill these cases in. However, in the presentation we move on. And for example then, if you look at alpha equals root 3, which also happens to be irrational, and n equals 10, we could choose a equals 4 and b equals 7. And that's because, well, root 3 is about 1.7 something, so 4 times root 3 would be 2 times 1.7 is 3.4, times 2 is 6.8, and all the fractional stuff that goes beyond that ultimately turns out that 4 times root 3 is approximately 6.928, and certainly if I subtract that off of 7, I get something that is smaller than 1/10. Now, this is something that I found experimentally, of course. What Dirichlet's approximation theorem does is Dirichlet's approximation theorem guarantees that something like this, an approximation like this, will always work. And that gets us to the other part that we wanted to discuss in this presentation, and that is sequences. Formally, a sequence an is a function from the positive integers to the real numbers, and that's not really how you want to talk about these things informally, and that's really how we want to think about these things, is that a sequence is a list of numbers, a1, a2, a3, and so on, and so on. So for example, if I set an to be -1 to the n, I get the sequence n equals 1, I get -1, then I get -1 squared, which is 1, then I get -1 cubed, which is -1, and it keeps alternating like that. And that, for example, is the standard way to encode alternating negative signs. If I set an equal to this thing, and we will see where this sequence comes from when we talk about Fibonacci numbers, but if I set an to be 1 over root 5 times big parenthesis 1 plus root 5 over 2 quantity to the n plus 1 minus root 5 over 2 quantity to the n, big parenthesis closes, I get a1 equals 1. And a1 equals 1, that sounds okay, because when n is equal to 1, what do I get here? The plus root 5 and the minus root 5 cancel each other out. And that, therefore, is not correct. Hang on. And we're back. And, well, the problem was a typo. So I want an to be 1 over root 5 times 1 plus root 5 over 2 quantity to the n minus, not plus, minus. And then we have 1 minus root 5 over 2 quantity to the n, and big parentheses around the whole thing. When that's the case, well, then a1 is equal to 1, and now that makes sense, because 1 minus 1 goes away in the numerator. Root 5 minus root 5 is 2 times root 5. Divided by 2 gives us root 5, and 1 over root 5 multiplied with that gives us a 1. Okay, now a2, well, I mean, I'm just showing you how to plug in numbers into a function, but let's see where that goes. a2 would be 1 over root 5 times this quantity squared minus this other quantity squared, and if we work that out, well, what do we get? We get 1/2 squared, which is 1/4. We get 2 times 1/2 times root 5 over 2, so that would be just root 5 over 2. And then we get root 5 over 2 quantity squared, which is 5/4, minus, and here we get 1/2 squared, which is a quarter, 2 times 1/2 times negative root 5 over 2, which ends up being root 5 over 2, and negative root 5 over 2 quantity squared, which is 5/4. And when we look at that, the 1/4 cancels with the 1/4, the 5/4 cancels with the 5/4, the square root 5 over 2 minus square root 5 over 2 gives us square root 5 again, and divided by root 5 gives us a 1. Okay, well, so there's another integer. Great. a3, well, it's the same story with this thing, only with the third power, right? Well, let's see what that gives us. That gives us still the 1 over root 5 in the front. 1/2 cubed is 1/8. Then we have 3 times 1/2 squared times root 5 over 2, so that would be 3 2's in the denominator, so the denominator is 8. We have the 3 and we have the root 5 from the root 5 over 2. Then we have 1/2 times root 5 over 2 quantity squared, and the whole thing times 3 with the coefficient from Pascal's triangle, so we end up with 3 2's in the denominator, which means the denominator is 8. We have the 3 from Pascal's triangle, and the root 5 quantity squared is 5. And then we have root 5 over 2 cubed, and that is 5 root 5 over 8. And then we have minus, well, minus the same thing. The only thing that changes is that every second term is negative, because, right, the 1/8 was the 1/2 cubed. This one has a root 5 over 2, a negative root 5 over 2 to the first power, so that gives us the minus sign here. This one has a negative root 5 over 2 in the second power, so we keep the plus. And this one is negative root 5 over 2 to the third power, so that's the minus here. And now we look at cancellations again. Well, we've got a 1/8, that goes away. We've got 3/8 times 5, whatever that is, it goes away. We've got 3/8 root 5 minus 3/8 root 5, so that would be 6/8 root 5, or 3/4 root 5. we've got 5/8 root 5 minus negative 5/8 root 5, so that would be 10/8 root 5, which is 5/4 root 5. Well, 5/4 root 5 from here plus 3/4 root 5 from here is 8/4 root 5. And 8/4, of course, is 2. So that's 2 times root 5 divided by root 5, and that ends up being 2. Now, whoa! We'll see soon that, in fact, all the elements of that sequence are integers. This is not an accident. This is something that was planned despite the hiccups on the previous panel. However, do you see a way to prove that right now? I mean, this is one of those things where you realize all of a sudden that proofs are probably something that we really need to take seriously, because after all, we could claim here and have reasonable data to suggest that this sequence is a sequence of integers, but how do we know? How do we not know that by the 1.5 millionth term there is some kind of a fractional part here? And this sequence is called the Fibonacci sequence. We'll talk about it in a later presentation. Okay, so what else? A geometric progression is another type of sequence, and that's a sequence of the form a times r squared, a times r cubed, a times r to the fourth, and so on. And so basically it is something that grows in as powers of r. It's basically exponential in r here. And that is, its formula is a(n) is a times r to the n. So it is something that is called geometric because one way to motivate it is via certain geometric arguments, but overall it is, if you come from calculus, you could also call it's something that is exponential. Okay, so what can you do with sequences? Well, one of the things that is on certain kinds of intelligence tests, if you will, is that you can conjecture a formula for a sequence, or at least try to find the next term. And so, for example, if I give you the sequence 5, 7, 9, 11, well, okay, those are all odd numbers, which means that the next term is 13. And as a formula, what would I need? I need odd numbers. Well, odd numbers are of the form 2k plus 1. And if k equals 1 is here, then this should actually be 2k plus 3, I think. And if I write that down as a sub n, well, then it's 3 plus 2n, but that's the same thing as what I've just said. All right, so first intelligence test passed here, right? Well, great. Okay, now let's take a look at this sequence. Starts with 6, then you get 9 halves, then you get 27 over 8, then you get 81 over 32. I mean, that, okay, what do we see here? Okay, 9 is 3 squared, 27 is 3 cubed, 81 is 3 to the fourth. So it's something that's geometric, probably. But 2, well, 2 is not 2 squared or anything. 8, well, okay, 8 is 2 cubed, so let's see, 2 is half of 4. 8 is half of 4 squared, 32 is half of 4 cubed, so that means it's something like 2 times 3/4 to the n. Actually, it's 8 times 3/4 to the n. I got the 3/4 right, but then somehow lost it on the rest of this stuff. And why is that 8 times 3/4 to the n? Because this is actually already the second term, right? This is not the first term, it's the second term. Yeah, and then the pattern actually fits. Now, the reason why I said at the beginning that these are so-called intelligence tests is because really the pattern has to be something that up to a certain degree has to be rigged in order for you to predict the next term of the sequence. So, for example, if I give you, and that's a geometric progression then. Okay, so if I give you this sequence, 2, 3, 5, 7, 11, 13, 17, and so on, can you predict the next number? Well, you'd already have to be into number theory to realize that these are prime numbers, so it's the sequence of the prime numbers. And that would mean that the next number is 19. But the interesting thing is there is no formula for the sequence of the prime numbers. There is no formula that says this is what the nth prime number is going to be. This is one of the reasons why internet encryption remains safe, because it's not just hard to factor numbers, it's even really, really hard to find prime numbers that are large. And so, yeah, let's see. So we end with the following. And again, the overall topic here is sequences. And I just want to give you as many examples of sequences as possible. And so here's the definition from set theory. And that is that a set C is called countably infinite if and only if there's a one-to-one and onto correspondence between C and the positive integers. So basically you can map the positive integers to C and capture everything. And that means that a set is countably infinite if and only if its elements can be listed as a sequence. And a set is called countable if it's finite or countably infinite. So countable sets are basically sequences. Countable sets are sets where we can just list the elements. So, well, that's all well and good, and then of course we can think of some sets that are obviously sequences, such as the positive integers. Well, that's not that hard. But one of the really interesting facts, where we're not going to go into formal proof, but one of the interesting facts really is that the rational numbers are countable also. The rational numbers can be written down as a sequence. And that at first doesn't make any sense whatsoever, because after all, we typically envision the rational numbers on the number line, and there is no first rational number, there is no second rational number. We don't know how to count those things. But if you envision them a little bit differently, if you put numerators on the x-axis and denominators on the y-axis, well then 1 over 1 will be the first rational number, 2 over 1 is the second rational number, 1/2 is the third rational number, 3 over 1 is the fourth, 0, well, okay, 2 over 2 is not 0, but you see 2 over 2 would be 1, and I've already counted it. So I'm going to use stuff where it repeats to count stuff that I haven't counted yet. So I would put 0 here. Here's 1/3. 4 over 1 we haven't counted yet, so 4 over 1 goes here. 3 over 2 we also haven't counted yet, so that goes here. 2/3 we haven't counted yet, goes here. 1/4 we haven't counted yet, goes here. And so now here, of course, would be 5 over 1. Then we would have 4 over 2, and 4 over 2 is 2, which we already have counted, so we would say -2 here. 3 over 3 would give us 1, and we already have that, so we could say -1. And so we would just keep on counting, and as long as we find a new positive fraction, we put that in the sequence. If we find a positive fraction that we already have seen before, we look for the corresponding negative, we put that in, and if the positive as well as the negative fraction already are in the sequence, we just skip. And in that fashion, we can, yeah, okay, 5 over 1, -4 over 2, right? And then it just continues like that. I don't know, my keyboard's stuck, I think. But basically in this fashion, we can count all the rational numbers. And, well, that is one of the strange things now about mathematics. You talk to someone in the calculus sequence and tell them that the rational numbers can be listed as a sequence, and most likely they're not going to believe you, and for good reason, because this sequence here has nothing really to do with the natural order of the rational numbers. It is just something that shows that in abstract mathematics, things are sometimes not quite as they seem. Okay, so what we have here is a first presentation, and the underlying current in these presentations are that we talk about numbers and that we have to prove what we have to do. And I've combined several sections of the textbook here, of course, so go through the text also, do some homework problems, get yourself used to proofs, and I'll see you in the next presentation. Until then. Can actually be proved, and actually has to be proved. But in this course, we will use this as an axiom, and the quick justification I gave is probably as good as it gets here, and it's fairly convincing. I mean, you've got finitely many possibilities, and one of them will be it. And using the well-ordering theorem as an axiom is also often done, so we are not losing anything here on the formal side. Okay, so the number system that we are most familiar with certainly are the real numbers. And we're just going to assume that we have some idea what the real numbers are, because we're really not going to work much with the real numbers. And we're going to call a real number rational if and only if it's a fraction. which is if and only if there are integers, numerator, and formal constructions. I've got another course for you. It's called Fundamentals of Mathematics. The slides are and the videos are on my website, and I've even written a book that you can buy. Okay, so number systems. Basically, the integers are just the whole numbers. They are the numbers in a set that counts 0, 1, 2, 3, and so on, but which also includes the negatives of these numbers. And that definition is certainly very, very informal, but we do need a starting point. And our starting point will be that we assume that we know what integers are and how they work. So I'm not going to define what addition and subtraction is. I'm not going to define what multiplication is, and so on. And you may think, wait a minute, we have to define that. And yes, technically we would have to define that, and that's one of the things that the Fundamentals of Mathematics course is about. So we assume that we know addition, multiplication, and ordering, and all those other things. And well, then we can also state the following. It's called the well-ordering theorem, and that well-ordering theorem says every non-empty set of positive integers, so if we start at 1, 2, and so on, every non-empty set of these things has a smallest element. That also feels very reasonable, because if you give me a set of positive numbers, I pick one number, and if that number is not the smallest number, well, I've got only finitely many possibilities underneath that number. I check them all, one of them will be the smallest element. So it is a bit surprising that in a more formal introduction, when you actually construct the integers in set theory, that this can... Welcome to the first class in this number theory course that actually does some content. This is the first class where we get our hands dirty. We'll be talking about a few proofs also, because certainly in an advanced class such as this one, anything that we claim has to be proved or at least justified in a certain way. And we'll be talking about numbers and sequences here. Well, so first of all, you could say, well, it's no surprise that we talk about numbers, because what other than numbers would number theory be about? But we're already lumping in sequences here, because we need sequences of numbers anytime we talk about more than just one number. Number systems are needed as the surrounding universe for our arguments, but we'll be informal here in introducing the number systems. And if you really are interested in the denominator, so that the denominator is not 0 and x is the quotient of numerator and denominator. The set of rational numbers will be denoted Q for quotient. The set of real numbers will be denoted R for real numbers. The set of positive integers will be called Z+. And if you're wondering about the Z, well, that Z actually is, well, the word integers doesn't start with Z. We know that. Z stands for the German word Zahlen, because apparently the notation was invented in Germany, I would think. And then taken over by other mathematicians here. Otherwise, we would probably call these things I, but once something has become fairly customary in mathematics, we stay with it. Okay, so positive integers are Z+, and